still talking about implicit differentiation, but today we're going to kind of bring in the derivatives of the inverse trig functions. So first of all, let's think back to pre-calculus when we first learned the inverse trig functions. When we first learned about them, we learned that we can really only take a small piece of the inverse sine, inverse cosine, and inverse tangent and call it the inverse function, because otherwise it would not pass the vertical line test and we couldn't call it a function. So that small piece of inverse sine, for example, is the part of the relation that lives between negative pi over 2 and positive pi over 2. Inverse cosine is between 0 and pi, and inverse tangent is between negative pi over 2 and positive pi over 2, but on that one, not including the endpoints because we have asymptotes on those, right? So that's just, these pictures are just kind of review of what those looked like when we learned about them in pre-calc. And so now we're thinking about calculus, and we're thinking about derivatives of inverse sines. So first of all, if we think about differentiating sine y equals x implicitly with respect to x, the derivative of sine would be cosine. So we'd have cosine y, and then chain rule, derivative of y is dy dx equals, and then on the other side of the equal sign, we have the derivative of x is 1. So again, right now, taking the derivative of this, dy dx of the left side and dy dx of the right side, and we get cosine y dy dx equals 1. And then if we solve for dy dx, we would divide both sides by cosine y, so we get the derivative of y with respect to x is 1 over cosine y. Then we think about our Pythagorean identities, the big Pythagorean identity in particular, which is this one, sine squared theta plus cosine squared theta equals 1. Since we have cosine y in our denominator, if we take that right here and we solve it for cosine y, we get cosine y is equal to the square root of 1 minus sine squared y. So then we take that and we substitute that in right here for cosine y, and we get dy dx is equal to 1 over the square root of 1 minus sine squared y. But then finally, we go back to the original equation that we were given, which was sine y equals x. And so we replace sine squared y with x squared. So we end up with the derivative of y with respect to x of the inverse sine function as 1 over the square root of 1 minus x squared. So basically those inverse trig derivatives come from implicit differentiation and the Pythagorean identity and some substitutions. So you could go through a similar proof to find the derivative of inverse cosine and the derivative of inverse tangent, but those three derivatives are given for you here in this box right here in your notes. So those are some important derivatives that you want to maybe add to your pile of flashcards in terms of working on memorizing. So now let's apply these three new derivatives that we now know what they are. So in example 1, we want to find the derivatives for equation A and for equation B. So equation A is y equals the inverse tangent of x squared. In equation B, y is equal to the inverse tangent of x squared. All right, now I explicitly gave you these two because they're similar yet they're different, right? In the first equation, it is the inverse tangent that is being squared. In the second equation, it is x that is being squared inside of the inverse tangent function. So what I want to point out about these two equations is that both are compositions of functions. Which means that both require chain rule. But obviously, they will not be the same answer when we are done because the inner function and the outer function are not the same for these two. So we're going to go back to our chain rule roots when we first learned the chain rule, and we're going to identify our outer function and we're going to identify our inner function. So for letter A, I would say that my outer function is that something is being squared, right? So my outer function is y equals u squared. And then my inner function here is going to be what's inside the parentheses that is being squared. So my u, my inner function, is going to be the inverse tangent of x. So if I want to find my derivative, or my y prime, remember that if I'm doing chain rule, I'm first differentiating the outer function at the inner. So that's just going to be power rule. I'm bringing down the 2, and then I'm changing the exponent to a 1, and what's inside the parentheses, the inverse tangent of x, is going to stay exactly the same. But now I have to multiply by the derivative of the inner function, and the derivative of inverse tangent x is 1 over 1 plus x squared. And so then I write my final answer as y prime equals 2 times tangent inverse of x divided by 1 plus x squared. In my second example, this time my outer function is the inverse tangent, right? And my inner function, my u this time, oh, sorry, I should have put y equals. And my inner function this time is u is x squared. So when I take my derivative of y prime, I first have to differentiate the outer function at the inner. If my outer function is the inverse tangent, then I know I'm going to have 1 over 1 plus my inner function squared. And my inner function is x squared. But then I have to multiply by the derivative of the inner. The derivative of x squared is 2x. So my derivative ends up being 2x over 1 plus, and then x squared squared, I can write as x to the 4th power. This time we have the inverse sine of 2x plus 1. So again, we have an outer function and we have an inner function. Our outer function this time is y equals the inverse sine of u, and our inner function is that u is equal to 2x plus 1. And again, I'm showing every step here. If you can differentiate this without identifying the outer and the inner, which is the point that we always want to get to when we're using the chain rule, that's fine. But since we're doing these inverse trig functions, I'm just showing you every step to get you used to using the formulas. So my y prime is going to be equal to, first, the derivative of the outer function, which is inverse sine. And I know the derivative of inverse sine is 1 over, and then it's going to be the square root of 1 minus, and then whatever my inner function is squared, right? Because it's the derivative of the outer at the inner. And my inner function is the 2x plus 1. But then I have to multiply times the derivative of the inner function, and the derivative of 2x plus 1 is 2. So now I can clean this up, and I can write this as y prime equals, in the numerator, 2 over the square root of, and you could FOIL out 2x plus 1, quantity squared, and combine like terms, but in this case I'm just going to leave it in the parentheses like that. The next example, we have an inverse cosine as our outer function. And this one actually has a composition of 3 functions. Right? So our outer function is the inverse cosine. Our middle function, in this case, would be u equals e to the, and now I need another variable, so we'll go with w. U equals e to the w. And then our innermost function is w, which is the exponent on the e, is 2x. So when I find my derivative this time, my y prime, Start on the outside, work your way in. That's always how chain rule works. And you just keep multiplying by the next inner function's derivative by the next inner function's derivative. So start with the outer function. The derivative of inverse cosine is going to be 1 over the square root, and we need a negative in front of that square root, right? So 1 over the negative square root of 1 minus that inner function squared, right? And so the middle function that's inside is that e to the w, or e to the 2x power, okay? But then I have to multiply by the derivative of e to the 2x, which is e to the 2x, but then I have to multiply by the derivative of 2x, which is 2, right? Because I have to make sure that I'm multiplying, I'm doing the chain rule multiple times here. So my y prime is going to be equal to 2e to the 2x divided by the square root of 1 minus e to the 2x squared. And if I wanted to, I could multiply these two together, 2x times 2. So I could write my final answer as y prime equals 2e to the 2x over the square root of 1 minus e to the 4x power. Oops, sorry, forgot that negative sign in front of the radical again. Shame on me. There we go. Cosine has the negative sign in front of the radical. Sine does not. So 2e to the 2x over the negative square root of 1 minus e to the 4x. Our last example today takes us back to the lesson that we did at the end of our 3.1 through 3.5 plus chapter, where we took notes on the derivatives of inverse functions. So in example A, it says, suppose f is a one-to-one differentiable function and its inverse function, f inverse, is also differentiable. Use implicit differentiation to show that f inverse prime of x, so the derivative of f inverse prime, or excuse me, the derivative of f inverse is equal to 1 over f prime of f inverse of x. All right, and I'm going to put a little note here. We derived this formula in the derivatives of inverse functions notes. Which was chapter 3.1 through 3.5 plus, right? And that was the plus part of that chapter because for whatever reason, they don't include a section on derivatives of inverse functions in your textbook. However, it is on the AP test. Okay, so for part A, let's rederive that formula because extra practice is good practice. So we start with the fact that based on the definition of an inverse function, f of f inverse of x should give us back x, right? If two functions are inverses of each other and we do the composition, we should just get back x, right? That's a rule that we learned way back in Algebra 2. So now if I am going to differentiate implicitly, so I'm going to take the derivative with respect to x of the left side, inverse of x. And I am going to take the derivative. You could write dy dx, but we don't have y's, we're using f of x, so that's why I'm just using the d dx notation. So the derivative with respect to x of x. Okay, so now on the left-hand side, keep in mind that I have a composition which requires chain rule, right? So we differentiate the outer function at the inner. All right, so this is going to be f prime of f inverse of x, that's the derivative of the outer at the inner, times, now we have to do the derivative of the inner, and the notation of f inverse of x derivative is a little goofy because we can't use the prime on the inside because we already have the inverse symbol, so we write it like this, f inverse of x derivative. We write it like that, okay? So that's the derivative of the outer at the inner times the derivative of the inner. And then on the other side of the equal sign, the derivative of x is 1. So then now we just need to solve this for the derivative of f inverse. So if we want to get that alone, then f inverse of x derivative is going to be equal to 1 divided by f prime, or sorry, f, the derivative of, there we go, f inverse of x. Okay? F prime of f inverse of x, I guess is what I was trying to say. Okay, so that's our part A. Then part B asks us to use this equation that we just developed and says if f of 4 equals 5 and f prime of 4 equals 2/3, find f inverse prime of 5. Okay? So first of all, for part B, if f of 4 is equal to 5, then f inverse of 5 is equal to 4. Okay, and that's just based on the definition of an inverse. So I'm going to start with, if I want to find f inverse prime of 5, so then f inverse prime of 5 is going to be equal to 1 over f prime of f inverse of 5, right? Well, this is going to be equal to 1 over f prime of f inverse of 5, I just wrote on the left-hand side of my screen, is 4. And they told us that f prime of 4 is 2/3. So this is 1 over 2/3. And 1 divided by 2/3, keep switch flip, gives me an answer of 3/2. So f inverse of 5 prime, the derivative of f inverse of 5, is equal to 3/2.